So this is basically when we turn on the electromagnetic field, this factor picks up this factor now, but this factor does not depend on the path. It just depends on the endpoints. So now let us look at what the total path integral would look like before and after turning on the magnetic field. So the path integral before turning on the magnetic field will have contribution from all the paths which go below. Okay, so all the paths, or let's take the above path. So all the paths which go, through the upper slit. Okay, so all the paths that go like this. So it can go like that, but it goes like this. It can go this and do like this. So these are all the paths that go above. So this would be one contribution to the path integral, and it'll be, of course, weighted by the action along all these paths. And then there will be another contribution, which would be from all the paths which go below and again, this will be weighted by the corresponding actions. So this is our path integral before, but when we turn on the electromagnetic field, what will happen is that, this guy will still be there. So I'm just going to copy and paste. But it's going to pick up a new term, a new factor, I should say. And that factor is going to be exponential. So this is inside bracket. And outside the bracket, there will be an exponential of IE divided by H bar C of all the line integrals from all the paths above, but of course they're path independent, so they will only depend on this, on the initial and the final point, which we are fixed. So they will come. So this will factor out of the path integral. Okay. I'm still writing it above, although you will see that this is not necessary, because it only depends on the endpoints. But yeah, and then we also have the term from below. And then it's going to be multiplied now by a factor of IE over H bar C, integral from x1 to xn, again, A dot ds below. Okay. So now you see that what we have is sorry, I misspoke. I think it's important that this integral, keep in mind that we are doing it for all the paths above and all the paths below here, because if they were the same, then of course there would not be a magnetic field. So A for the paths below would be different for A for the paths above, even though they don't depend on the path itself, but the A itself above would be different from A below. Okay, we don't really need the explicit value of A for this argument, although it can be easily derived. So now look at the amplitude. So the amplitude after we have introduced the electromagnetic field, has a factor which is has a term which is A above times say C, A. C is this factor. And then it has a term which is A below, and then C below. So if I look at the probability, I have to square this. And if I square this, what will I get? So these are phases, right? As you can see, these are just pure phases. So there'll be terms in which the probability, it'll be just like A above squared plus A below squared. But then there'll be terms in which it'll be A star above, A below, and C star above, C star below, and its complex conjugate, right? It has to be a real number. Now, if I look at what this thing is, CA star CB, then what we see is that it'll be E minus it'll have an exponential and the argument of the exponential. So the argument of, say, C star A, CB, will have E over H bar C. Well, there'll be an I here, and then inside there'll be an integral from x1 to xn, and A would be given by above. And because of the complex conjugation, there will be a minus sign here, and there'll be E divided by H bar C, and then integral from x1 to xn, and then A dot ds below. But together, this is just an integral which is a closed integral, a closed path integral, closed line integral, right? And then we can use Stoke's theorem, and this just becomes the curl of A through the surface that is enclosed by this path. In this case, something like this, like this surface. And of course, this surface does have a magnetic field threading through it. So this is B, and therefore we have IE by H bar C B dot ds, which is just IE H bar C, the magnetic flux. And now what we can do is that, the magnetic field is a variable we can control. So if we control the magnetic field, we see that the interference pattern will change because, this thing will change. And because it's an exponential, it's in an exponential with I, you will have a periodic interference pattern. So as we vary the magnetic field, the interference pattern will change with the fundamental magnetic field periodicity, fundamental, period. Let me put this in quote, which is, what will be the period? It'll be E, the condition will be given by E H bar C phi B equal to 2 pi, right? Because in the exponential, the argument will be periodic if the argument of the exponential changes by 2 pi. So this is If you solve this, we get a fundamental unit of magnetic field which is given by 2 pi h bar c divided by the charge of the electron, the modulus, and this is given by 4.135 into 10 to the power minus 7 Gauss. Gauss is a unit, so it's small. Gauss centimeter squared. Okay. So this is the Bohm-Aharonov effect, or the Aharonov-Bohm effect, in which a magnetic field an electron can sense the presence of a magnetic field in a region it doesn't have access to. And you can show that it does so by varying the magnetic field, which leads to a change of the interference pattern. And this has been experimentally verified, and poor Aharonov still hasn't got the Nobel Prize though. Okay, so any questions? It's perfect timing. It's 6:20. All right, any questions? Nahi, Shujosh is not here. That's why it's so quiet today.
Sir, it would be nice if you just could summarize in short the whole of Aharonov effect.
Yeah. So, let's go to the picture first. So, if there was no magnetic field, there would be some interference pattern here, right? Between the electrons going through this way and this way. And we could calculate that interference pattern using the path integral, because we could calculate their action. And then to calculate that action, we would need the free Lagrangian. Now, when we turn on the magnetic field here, the Lagrangian changes by this term. And therefore, the action, which is dependent, of course, the action is a functional, so it depends on the path. So every little, for every little path of the segment, we can calculate some action, right? And that is basically this little action. So this notation means that this is the action associated to a small straight path from n-1 to n, where n-1 to n means from this time and this position to this time and this position. So if you turn on the electromagnetic field, this contribution to the action will change by this term. Okay, is that clear, Nahi?
Yes, sir.
Now the guy is a time integral, but because of the particular form of the Lorentz force law, we can change this time integral into a line integral. Okay, and this is the key. So now what we can say is that we can take any path which, say, goes above and compute the whole action that is going to contribute to the path integral for that path. So that contribution will be made out of a lot of small actions, and we have to consider their products. Of course, the product, when it goes into the exponential, it becomes a sum. So each of these actions will now have, will contribute a little bit of this, which of course is this. But now we can sum all of these guys, and that sum is going to give you an integral from x1, the initial position, to the final position. But we know that this integral is independent of the path as long as the path does not cross a region of non-zero magnetic field. And of course, we are taking a path which is only going, it is not crossing this, it's just going above, okay? So we can then factor this out of the path integral. So this thing does not depend on the path. It just depends on the fact that it's on its endpoints and the fact that none of these paths cross the magnetic field. So, so that's what I'm saying here, why it doesn't, because if there is no magnetic field, this closed line integral is 0, and therefore we can divide it into 2 line integrals, and we can continuously deform one into the other. Now, in the path integral, there will be two types of contribution. Contributions from the paths which go above the cylinder, and contribution from paths which go below the cylinders. If we now turn on our the magnetic field, then each of these things, the above guy will now pick up this factor. And in this factor, of course, this path, this contribution is independent of the path, but it depends on the fact that all the paths goes above the cylinder. And that has to do with the fact
Sir, why is that? I couldn't get it.
Because
like, why does A depend on above or below?
Oh, because then this would not be path independent. And this fact is encoded in the value of A. A above the cylinder is different from A below the cylinder, and that's what it's give. But this integral is still independent of the path. But it depends on whether the path goes above or below. Okay?
Okay.
So, you can work this out. I can send you the exact value of A, and you can work this out. And then there'll be all the paths, contribution to the path integral from below, and then there'll be another factor, but this factor, the integral, will depend only on the fact that the paths are going below the cylinder, but it does not depend on the details of the path, apart from this fact. So now our amplitude has this form, which is A above, A below, and these 2 phases. These are the phases, these 2 phases, this guy and this guy. So now if I compute the probability, then I see that in the interference terms, I get this interference of the 2 phases. Now I'm looking at the argument of the phases of the exponential, and I can combine those 2 above and below to a loop integral, a line integral, a closed line integral, and then using Stoke's theorem, I can turn that into an integral over the magnetic field, which just gives me the magnetic flux. So this is this is going to be exponential of this guy is going to appear in the over here and in the complex conjugate. So we'll have some sine or cosine coming from that. And therefore, it'll be periodic in the period in this magnetic field unit. Well, the fundamental period is going to be given by this, okay? And this is basically the Bohm-Aharonov effect.